Hello and welcome to this short presentation relating to calculating volumes of prismatic sections. A prismatic section being a constant section shape. So for example, calculating the volume of this tube or pipe section shown in the sketch here would be calculating the volume of a prismatic section. So let's consider the unit of volume. So volume is a measure of how many cubic units an object contains. So 1 cubic meter, short form shown here, is the volume contained in a cube whose edge is 1 meter. As shown in the sketch here, each of the sides of this cube are 1 meter, so the volume of the cube is 1 cubic meter. Considering the rectangular solid shown in this sketch here, it's divided into 3 layers. 3 layers shown here of small cubes. Each cube has a volume of 1 meter cubed. And as there are 5 multiplied by 4 cubes in each layer, that's the 5 meters here multiplied by the 4 meters here, then the total number of cubes in this volume is 5 multiplied by 4 multiplied by 3. So that's a volume of 60 meters cubed. Within this presentation, we're only calculating volumes of prismatic sections. In other words, volumes of prisms. A prism is defined as a solid which has a constant cross-section. And each of the examples shown here are prismatic sections. The first is a rectangular prism, and to calculate the volume, it's simply the area of the base, A, multiplied by the length or vertical height shown here, labelled L. For the cylindrical prism, shown here, again it's the area of the base, circular area here, multiplied by the height. And for the triangular prism, again it's the area of the base, multiplied by the vertical height here. So the volume of a prism is simply the area of the prism multiplied by its length or vertical height. In symbols, volume V is equal to the area A multiplied by the length L. Here are some further prismatic sections. I've already mentioned the cylindrical prism on the previous slide and the triangular prism. But here's an I-section prism, rectangular prism here, subject to a load P, something we reviewed in our stress and strain lecture, and a square hollow section prism, actually defined as a stanchion, again in our previous lecture on stress and strain. Here's example 1. We're asked to calculate the volume of the steel I-section beam shown in the sketch. This is the I-section beam here. This is a prismatic section. It's a constant section throughout its length. Notice all the dimensions are in millimeters here. So firstly, let's find the cross-sectional area of the I-beam. I'm going to break the I-beam into 3 rectangles. So the first one is the upper flange. We can see from the geometry that's 50 millimeters wide and 6 millimeters thick. So it's calculated here. Next, I've calculated the web, and the web from the geometry given is 88 millimeters deep by 6 millimeters width, shown here. Calculate the 88 millimeters here. It's the depth of the I-section, 100, minus twice the flange thickness, so minus 2 times 6 in this case. And finally, we've got the lower flange, which is 60 millimeters wide in this case, multiplied by the thickness of 6 millimeters. So add that into my calculation. So evaluating the area of the I-section is 1,188 millimeters squared. Now to calculate the volume of the I-beam, V, it's simply the area, A, calculated above, 1188 millimeters squared, multiplied by the length of the prismatic section, length of the I-beam here, and that's 300 millimeters given in the question. Evaluating the volume of the I-section beam is 356,400 millimeters cubed. That's a typical illustration of calculating the volume of a prismatic section, in this case an I-section. Just note for reference that the volume, 356,400 millimeters cubed, would actually be 0.0003564 meters cubed. So in other words, to convert from millimeters cubed into meters cubed, we have to divide by 10 to the power of 9. We'll now consider conversions between various units on the following slides. Let's consider SI unit conversions. We generally know that a length of 1 meter is equivalent to 10 to the power of 3 millimeters, or 1,000 millimeters. Conversely, 1 millimeter is equivalent to 10 to the negative 3 meters, or 0.001 meters. Our previous presentation related to areas, we know that 1 meter squared is equivalent to 10 to the power of 6 millimeters squared, or 1,000,000 millimeters squared. Conversely, 1 millimeter squared is 10 to the negative 6 meters squared, or 0.000001 meters squared. So when we're converting linear lengths, 1 meter is 10 to the power of 3 millimeters. When we're converting area, 1 meter squared is 10 to the power of 6 millimeters squared. So now when we're converting volume here, 1 meters cubed is equivalent to 10 to the power of 9 millimeters cubed, or sometimes stated as 1,000 million or 1,000,000,000 millimeters cubed. Conversely, 1 millimeters cubed is 10 to the power of negative 9 meters cubed. A very small number indeed. Although not an SI unit, we are allowed to use the litre, and often volumes are measured in litres. So, for reference, 1 litre is equivalent to 10 to the power of negative 3 meters cubed, or 0.001 meters cubed. 1 meter cubed is equivalent to 10 to the 3 litres, or 1,000 litres. We could also write 1 litre as equivalent to 10 to the power of 6 millimeters cubed, millimeters cubed, or 1 millimeter cubed is 10 to the negative 6 litres, as shown here. So be aware of those general conversions, because some of them will occur in the work we're going to review in this and other presentations. And again, just for reference, I'm referring to cancelling unity brackets here. This is something we reviewed in a previous presentation, but unity brackets offer a very structured way of converting between various units. Just very briefly show an illustration here. We want to convert from millimeters cubed to meters cubed. Here we've got a volume that's 356,400 millimeters cubed, and we want that in meters cubed. Then we need to use unity bracket. In this case, the unity bracket is 1 meter divided by 1,000 millimeters. That is unity. In 1 meter, there is 1,000 millimeters. And recalling from previous work, they're cancelling unity brackets. So we have to cancel the millimeters on the top. So that means we have to put the millimeters on the bottom in the bracket. And as our unit is cubed here, then we need to cube the unity bracket. So the conversion of 356,400 millimeters cubed into meters cubed, we have to divide by 1,000 cubed, or 10 to the power of 9. So converting from millimeters cubed, that becomes 0.0003564 meters cubed. And of course we can convert other units. This is meters cubed to litres here, 1.2 meters cubed into litres. This time our unity bracket will be 1,000 litres is equivalent to 1 meter cubed, as we looked at on the previous slide. And here the meters cubed on the top will cancel with the meters cubed on the bottom. So that means in this case we'll be multiplying by 1,000. That means we can convert our 1.2 meters cubed into litres. It's 12,000 litres. And here are other unity bracket conversions for your reference. There is a specific presentation on unity brackets if you require further information. Here's some tutorial questions related to calculating the volumes of prisms. Question 1, we're asked to find the volume of a rectangular block having a geometry 2.8 meters wide, 2 meters deep, and 3.2 meters in length. In question 2v, a steel bar has the cross-section shown in the sketch here. If it's 9 meters in length, we've got to calculate its volume. The answer for question 1v is shown here in meters cubed. The answer for question 2v is shown here in millimeters cubed. I would encourage you to stop the presentation and attempt these questions, but the full work solutions will be shown on the following slides. Here's question 1v, solution. We have to calculate the volume of the rectangular block, given the geometry. The width is 2.8 meters. I've labelled that as B here. The depth is 2 meters. I've labelled that as D here. And the length is 3.2 meters, labelled as L here. To calculate the volume is essentially dimension B multiplied by D, and that's effectively the area of the base here, and then multiplied by length L. Inserting the values for B, D, and L, the volume is 17.92 meters cubed, to 2 decimal places here. The question states the answer to 1 decimal place. So essentially the B times D term is the area. Question 2v, given a steel bar has the cross section shown in the sketch here. If it's 9 meters in length, we've got to calculate its volume. So I've labelled dimension B here as 100 millimeters, that's this dimension here. Dimension R is the radius, 75 millimeters, shown here. And note that what I've labelled dimension D here, D is twice the radius, so it's 2 times 75 millimeters, 150 millimeters. So essentially what we're going to do here to calculate the area of the section is to break it into a rectangular section shown here. We can calculate the area of a rectangle from the formula base times height. And also we're going to have the area here of a semicircle, and again from our previous presentation on areas, area of the semicircle is pi r squared divided by 2. So we can calculate the area of the cross section A here. Inserting the values, we know B is 100, we know D from above is 150 millimeters, and we know the radius R is 75 millimeters, that's given in the question. Evaluating the area of the cross section is 23,835.7 millimeters squared. So to calculate the volume of the bar, it's simply the area calculated above multiplied by the length. We're given in the question the length is 9 meters. I've just converted that to millimeters here because my area is in millimeters, so 9,000 millimeters is the length. So to calculate the volume, it's simply the area, A, which is from above, multiplied by the length of the section, 9,000 millimeters. So the volume calculates to be 214.52 times 10 to the power 6 millimeters cubed now. Question 3v. A cylinder has a constant cross-section which is of a circle. The diameter is 2.8 meters and the length or the height is 1.2 meters. We've got to calculate the volume of this cylinder. Diagrammatic is shown on the right hand side here. In question 4v, A pipe has a dimension shown in the sketch here. Dimensions are in millimeters. We've got to evaluate the volume of this pipe. So we have the inside and the outside diameters of the pipe, and we have the length of the pipe. Answers to these questions are shown in the brackets. I'd encourage you to start the presentation and attempt these questions, but the full solutions are shown on the following slides. Question 3V, solution. In the question we're given the diameter is 2.8 meters, so D is 2.8 meters, it's the diameter of our circle, and we're given the length or the height is 1.2 meters. I've labelled it L here for length, 1.2 meters. Sometimes it's denoted as H for height, but are often interchangeable terms. So to calculate the volume of the cylinder, V is equal to the area multiplied by the length. The area calculation is pi d squared upon 4, shown here from our previous work. That's the area of the circular base. And then we multiply that area by the length. So inserting the diameter, it's 2.8 meters. Inserting the length is 1.2 meters. We can evaluate the volume of the cylinder. It's 7.389 meters cubed. The answer in the question is shown to 2 decimal places. Question 4V, here's the solution. So the question gives us the dimensions of the pipe, shown in the sketch here, and dimensions are in millimeters, of course. We've got to calculate the volume of this pipe. So the outside diameter, capital D, from our sketch is 34 millimeters. So we know our outside diameter. The inside diameter of the pipe, lowercase d, is 20 millimeters. We have lowercase d. And the length of the pipe in this case is 100 millimeters, so shown here. So to calculate the cross-sectional area of the pipe, first of all, we're using this standard formula from our previous notes, which is pi multiplied by, in brackets there, the outside diameter squared minus the inside diameter squared, all divided by 4. We've shown that equation previously in our Introduction to Areas presentation. Inserting the outside diameter, 34 millimeters, and the inside diameter, which is 20 millimeters, we can evaluate the cross-sectional area, in other words this area here, and that's 593.76 millimeters squared. To calculate the volume of the pipe, we know that the volume is equal to the area, A from above, multiplied by the length of the pipe given in the question. Inserting the values, the area from above, length of pipe given in the question, the volume of the pipe evaluates to 59,376 millimeters cubed. I will leave question 5V for you to attempt at your own pace. We're asked to calculate the volume of the angle section that's shown in the sketch. This angle section shown here. If the length is 120 centimeters. So be careful of the units. In the sketch here, the dimensions are all in millimeters, but the length is given in centimeters. So I suggest you now work out the cross-sectional area of the angle section, and then knowing the cross-sectional area and the length, you can find the volume. The answer is stated in the bracket here, but notice the answer is in meters cubed. I'll leave that for you to attempt at your own pace. Here's the bibliography used to help generate this presentation. I hope this has been of interest to you, and thank you for viewing.